So good morning, everyone. Good morning, good afternoon. So I'm Alex Nichol, technical marketing engineer, and I predominantly look after our routing or our software stack. And that's both within the data center, so your typical deployments in the data center, VPN, VXLAN, integration with overlays like NSX and such like that. But I also look after our roadmap around our routing stack. So you might see outside the data center, so we're talking here NPU-led, traffic engineering, and the VPN services that sit over top of that. So that's kind of the role of this presentation. What I'm going to talk about today is what we're terming as cloud-grade routing, or an iteration of cloud-grade routing, which is 3.0. And really, it's not an individual feature or a platform, but it's kind of a thought process or an architectural approach to kind of address what we're seeing as challenges being presented by the operators. Okay. So let's dive a little bit further. I think it's worth, before I go into the details of it, kind of like level set on terms of what problems do we see, or what problems are the operators telling us. I mean, I think some of these are quite obvious. As we all know, massive explosion of devices are now connecting to the network, right? Massive amount of users now connecting. The users are connecting with multiple devices themselves. So we're not just connecting with one device, a laptop, connecting with a tablet, your phones, your set-top box, your streaming device, and the overall data you're consuming, right, is getting richer and richer, which is driving up the whole bandwidth, right? So these are kind of obvious statements. Now, the point being to an operator themselves is that the challenge they're having is kind of twofold. One is, in general, the revenue are pretty much flat. So year on year, they're not generating any greater revenue, and that's down to multiple things, whether it be typical services we deploy and generate any revenue are being cannibalized by the cloud, or the new OTT service providers, but probably also the need for them to upgrade their infrastructure, right? So the CapEx costs are going up, and that's down to this new bandwidth growth they're seeing, where they have to upgrade their infrastructure, move from 10 gig speeds to 100 gig, even potentially even 400 gigs speeds. But probably more interesting is, along with the CapEx spend, is what they're also seeing is that OpEx spend is also continuously increasing. Right? I mean, generally, the thought process is that for every dollar of CapEx spend, they're spending maybe $3 to $5 of OpEx to actually operate and troubleshoot and manage that piece of infrastructure. And that's really down to the kind of traditional way they have rolled out services. Right? It's been very static, rather than what that's now needed is a more dynamic model. So what we're talking about here to kind of address these challenges is the thought process here is the existing routing models, the existing architectures that we're using just don't work, right? They become too costly, they don't scale very well, and they're too cumbersome. So what we're trying to do here is actually introduce some sort of cloud economics into a routing solution. So the first point here is looking at routing and addressing the performance by leveraging merchant silicon. So looking to build routing platforms based on merchant silicon. And that allows us to address the ongoing bandwidth demands I talked about year on year, right? So, and if we run along with the bandwidth that the merchant silicon delivers, we can then see a continuous reduction in cost per bit, right? With new iterations, new generations of silicon every 2 years, we'll see a dramatic cost per bit as the bandwidth or the port density doubles every 2 years, your cost per bit goes down as well. And that's only one part of that solution, right? The other part now is looking at the whole architecture of how we actually build routing topologies, right? Making use of that merchant silicon, yes, to get the bandwidth, but also there's a need to move to what we term as a scaled out architecture, right? Now, rather than the traditional, what we say is a scaled up architecture, what we're talking about now is moving to a scaled out approach. The point being here is kind of learn from the cloud, scale out, modularize, repeat, allow you to now deploy topologies for any size, whether it's small or large. At the same time, over the top of that infrastructure, look to commoditize the protocol stack, right? Reduce the amount of protocols running, simplify the services they're running as well. Not simplify the services here in terms of how they're implemented, not remove the services or go do away with certain services, but simplify how they're actually deployed, the control plane they're using, and the data plane they're using, right? And again, the whole point here is kind of going back to where Freddie alluded to, if we're going to really automate all this, we need to move to a solution where it's repeatable regardless of size and it's consistent, right? Same model everywhere, where possible. Now, with this type of architecture, and we'll go through the details of it, it really then means that automation becomes key, right? Because you're now talking about the potential with a scaled out architecture. You're going to have more nodes potentially in the network. So the whole idea of being able to need to automate becomes critical. So this is where we're talking about our EOS operating system. Now, what we're talking about now is deploying EOS with a full featured routing stack, but at the same time, deploying with all the other features that Fred has alluded to, right? In terms of single OS, so you get the API features, functionality, so you can do the automation with it. And we'll see in the demo as well, you can also still get all the streaming capabilities as well to give you visibility across the infrastructure. So that's kind of the pillars of what we term as cloud-grade routing. So let me dig a little bit deeper into why. I mean, sometimes it's obvious, sometimes ask the question, well, why merchant silicon? Why does merchant silicon make sense? And why does it now make sense when we start talking about routing? So if you look at typical routing platform, normally built around some sort of proprietary silicon, normally built around some sort of NPU design. And the point being with those types of platforms is you get a very flexible platform, right? Because it does a run to complete model, allowing you to do multiple lookups in the field. So the whole point then is you get a very flexible forwarding logic, right? Multiple encapsulations, multiple protocols to support, all the scale we require going forward. And that's really served us really well in the past 10 years, right? You can just think of the amount of features and functionalities some of these written protocols are now supporting. So it's been very flexible. It has delivered the services it required. But if you look forward and you look at the problem in front of us, the problem in front of us is all about bandwidth, right? And how to reduce cost per bit. And this architecture and this level of flexibility just counteracts the idea of reducing cost, right? Because if you build a very flexible platform, complex logic that comes with it, what you end up doing is a decrement in performance, a decrement in the power you're going to use because you're going to use more chips due to the lack of bandwidth you have in individual chips. So you're going to have to deploy more chips in your individual platform, more chips, larger platforms, therefore more real estate on your in your rack itself, right? And now this kind of graph kind of shows you the problem where I'm highlighting here is you think about the features and functionalities you've got in a router has evolved over the past 10 years through each of the generations, right? Massive amount of features, massive amount of protocol support, massive amount of encapsulation types, and it's evolved really well, right? But at the same time, over that 10-year period, you're only talking about, in those type of platforms, a 3 times performance increase over 10 years, right? Well, you're now at the point where, from a chip perspective, you're only looking at 1.6 terabits of throughput. And you can imagine, therefore, that's dramatically having effects on cost per bit, cost per port, the power envelope of the box as well. So take that approach, so that competitive sort of silicon NPU approach, and compare that to over the same 10-year period of merchant silicon growth, right? And this is like for like across the same period. What you can see here with the merchant silicon, and I'm comparing here to the June chipset, so the Jericho and Jericho Plus, Jericho 2. So over that same 10-year period, that merchant silicon has had 24-fold increase in performance. Right? 24 over the same 10-year period, to the point now you're talking about 7.2 terabits of throughput compared to 1.6 terabits. Right? A dramatic difference. Now you might say, well, that's fine, but that chipset is really fit for the data center. It's not a like-for-like comparison. It doesn't provide all the feature set. But at the same time as we've increased that performance, you've seen the increase in performance of the silicon over that 10-year period, the features and functionality of the silicon has also get richer, right? So if you kind of track, again, over the same rough period, through each iterations of the silicon, so go back to 2014, you had the original Arad chipset, 6 by 40 gig box, very much focused from a scaling perspective for the spine inside your DC, 40 gig aggregate, right? It was pretty fine for IP transit because it only really supported 64K routes. Next iteration, you moved to Jericho in 2016. You're now talking about, instead of 640, you've now got 600 gig per chip. But at the same time, you see the table sizes increasing as well, right? So you're now talking about 1.2 million routes. You now see a level of extra functionality we would term as typical routing functionality, MPLS functionality, VPN service. Jericho Plus, increase again now 9 ports of 100 gig, again increase in table sizes, increase in features and functionality. Right, so we're now at the point now with Jericho 2, 12 ports of 400 gig, 2.5 million roots. And then when we talk about our EOS software, that's 15 also million roots in the RIB. We've now got rich encapsulation, MPLS support, SR support, VXLAN, IPsec, MACsec, and you've got all the VPN services, right? So it does now become a like-for-like scenario. So you do get the performance and you do get the feature set at the same time. Okay, so again, this chipset and the Jericho chip is very much focused on routing, and that's why you've seen this iteration and new features added to it while the bandwidth is increased. So the adoption of merchant silicon on the platforms, right, is one part of the routing solution, right? But you also need to look at the whole architecture and how we're actually building things. Right? We need to move away from the whole complex protocol stack and what we term as scaled up approach. So scaled up is what we traditionally term to provide extra capacity and extra services in our routing, right? Where you have a large chassis and it's vertically scaled, fully integrated, single point of control, so the control plane and the management point, right? And the whole idea here is you end up with a Swiss Army knife of features and functionality, be able to deliver all the services you require. What the benefit being sold to you is that you do everything in one box, therefore you save your CapEx and your OpEx, right? But if you kind of look at it and what we've really learned and we've seen over the years, what it does mean is your whole bandwidth in each of the POPs is really determined by the fabric bandwidth itself, right? You're fixed until the next generation comes out, right? The resiliency becomes very hard, very complex, because it's a mix between hardware redundancy and all the complex proprietary software implementations you get with it, right? SSO, ISU, and everything else, and all the interdependencies that comes with it. And the other big problem with this whole solution as well is you're now concentrating your whole scale into one box. Everything's centralized, right? So then your scale then becomes defined by the lowest common denominator in the chassis. So what we're saying here is, well, this whole scale up multi-chassis approach has been very beneficial to us, right? We've come to a point, an inflection point where we need to look at something differently, right? Because as we all know and all have learned, the complexity involved, we start moving from generation to generation, we have mixed line cards, we have to worry about inter-feature dependencies, how the mixed line cards enter work, do all the features work at the same time, do I affect another feature with some other features running on another line card? The centralized state, really, as I say, is really based on the lowest common denominator. And again, if we have mixed line cards, it falls back to the cheapest and lowest line card. Right? So this whole model kind of needs to move forward, and it needs to move to a more incremental, modular, iterating, what we term as scaled out approach. So what do we mean by scaled out? So what we're talking about when we talk about scaled out is what we're talking here now is a disaggregated P, it could be PE node, it could be P node, right? It doesn't really matter. But they're all now built on a leaf spine topology. With the logic now being that your previous fabric and your chassis now becomes the spine itself. And it's just a high bandwidth, 100 gig, 400 gig Ethernet interconnect. Okay? The line cards are the leaf nodes. And the line cards could be fixed form factor, it could be chassis based on your features requirements, based on your access and port density requirements. And then now, the whole point here now is the resiliency now becomes hardware independent, right? Because you're scaling out, you get separation of state across different leafs. So your resiliency is now via hardware independence, and now you're reducing your reliance on all those complicated interdependent software solutions, right? Like SSO and ISU. Now, the whole point with this approach now is you've got elastic scale, right? You need more bandwidth in your POP, you just add more spines. You need more functionality or you need more access ports, you add a leaf, right? You need, and probably more importantly, you need extra functionality. So a new protocol comes along or a new port density requires, you can just add a new leaf to the existing fabric, right? So the whole point here is now you end up with a very consistent, repeatable model, right? Regardless of the size, whether it be small or large. And you also increase the radix of your solution as well, right? So you can actually extend your leafs. You can have remote leafs sitting in a remote site and bring them back in via extending 100 gig or 400 gig fiber. And then from a scale perspective, the scale now is distributed, right? The functionality only sits in one or two leafs. Therefore, the scale for that particular function only sits in those two leafs. It's no longer the lowest common denominator. It's spread and distributed across all the leafs based on the functionality and the features they're supporting. Right? So it allows us to scale a lot better allows us to actually iterate over time and upgrade over time without actually doing the whole rip and replace model we've done before. Right? So this is a continuous evolutionary model, right? Rather than the whole 5-year, 7-year rip and replace model we had before with the scaled up approach.
There is an initiative in the industry called the disaggregated routing. So it seems like you're following that pattern. So is your this scale out architecture cloud native based? Are you using microservices? The functions are all microservices based, or it's still monolithic software? You know?
No, the point here is this is what we're showing you here is it's a physical box running our operating system, behaving like your existing routers, but now you're building it like a disaggregated box, right? So instead of the line cards before where the function features would sit, the function features now sit on an individual leafs. Right? They're not sitting in the cloud, they're sitting on the operating system sitting on the box. Does that answer your question?
Okay, so so it's not cloud native based. I'm talking about the software. Is it EOS software?
It's EOS, no change in the exact same software running each individual box. And this is where we'll talk a little bit later on how the automation then becomes a key component.
So this EOS software, can I ask, is it like a disaggregated architecture, or is it one piece of software?
So EOS is our operating system that runs on any of our switches, whether it's sitting in the data center or sitting in this routing environment. It's just one, it's an operating system that's state-based, so individual agents. I can talk a little bit about it in a minute.
Okay.
But it's a single operating system that sits across every single platform, right? So the point, again, is the benefit of that approach is now, again, regardless of what leaf you deploy, what features you require, your software, your APIs, your telemetry, your visibility doesn't change at all because it's one operating system. But the operating system in this case is working and running independently on each individual box.
Okay.
Hey, Alex, I got a quick question in regards to the disaggregate part. And how are you guys doing the base, common set of feature components if you do have to do integration to something besides EOS for, a spine configuration or maybe a leaf that has a specific routing, a different set of routing requirements? How do you know from an upgrade and scale out? Since you're talking about scale out and you're not going to necessarily have all the same version release controls across the board, is the assumption that you have some sort of capability to check to make sure that you're going to be able to support the minimum feature that particular data center fabric requires? How are you guys going about that?
Again, it kind of falls. I mean, I don't know if I've confused the bit here, because this kind of falls back to some of the stuff that Fred was alluding to, right? We haven't changing that model, right? We can make use of it exactly what Fred discussed here, right? Because it's the same operating system.
All right. I just want to make sure that that's how you guys are viewing it through that lens for this portion here.
Exactly. The whole point here is like by being able to use the same operating system, we can leverage the same benefits we get everywhere else.
And is EOS running on white box, or am I buying Arista switches?
In this, I mean, it could be one or the other. We support both models. In this case, we're just explaining the situation where it's sitting on our box.
Okay, but I can run it white box if that's my model.
It's going to depend on the model you prefer, yes.
Okay.
Now, I suppose what's probably not pointed out, and maybe I should make clear here, is right the interaction between the leaf and spine is pure Ethernet and pure IP, right? So again, this is a very open system. So obviously, it could be our leaf box, but the spine itself could be any other vendor just running IP and MPLS if you want to run across the top of it as well. Right? Now, the other part of this as well, with the whole scale out approach, is going to be able to build a sort of repeatable and scalable physical topology. But the other problem you've got now is just the complexity we have in the software stack. Right? If you look at a typical PE node, in that PE node, you're going to be looking to run probably E-line services, so point-to-point, layer 2 VPNs, point-to-multipoint, layer 2 VPNs. You might also want layer 3 VPNs. You might also want multicast, all in that one box. And if you look at it, as we've been over time and over iterations, different vendors have different support for different models, different signaling, LDP, BGP signaled, different address families, right? Different forwarding models, different data planes. We've ended up with a very complicated stack, right? And you could just imagine in terms of how you would automate this, how you would troubleshoot it, how you would actually do any vendor interop, make sure the implementation was consistent across different vendors if you did want to do any automation service across the vendors, right? So the whole stack is getting too heavy, too complicated. So this is where we've done a lot of work in EOS and actually really built on the whole premise of what EVP and BGP provides us. So what we're talking about here now is a single control plane, okay? And on that single control plane, running all these services. So you can now provide E-line services, so what's termed as EVP and VPWS, so point-to-point service. You can do E-LAN services, EVPN, layer 2 VPNs. So now you have the ability to mimic what you would do with a traditional VPLS. You can now do that with EVPN. The difference now being is you also have the benefit of having a control plane learning via BGP. You also have multicast support in there. You also have layer 3 VPN support as well, right? So it's not just a layer 2 technology. It also gives you the ability to obviously advertise via BGP IP prefixes as well. And then you can also leverage some of the inherent benefits of EVPN itself, right? So if you look at EVPN as a standard, it supports a fully open, standards-based, all-active for multi-homing. So you can take your CE, multi-home it to your PE devices that are providing the layer 2 VPN service, whether it be point-to-point or point-to-multipoint, all-active support, active standby support, right? So it's a very standards-based solution, but the point is it's a lot cleaner, more consistent, and it's a single control plane. So a lot easier and simpler skill set to manage and control. And the same thing holds true if you look at now in terms of the whole MPLS transport. So when you're running those VPN services, you're going to run across MPLS traditionally. And traditionally, you would run that over MPLS, where you're going to again have a plethora of protocols running, right? You would normally have an IGP running, and then if you'd probably have some sort of separate, you wouldn't need a separate label distribution protocol, so LDP to distribute the labels. You need the IGP to then sync with the LDP because they're separate protocols. If you want any level of traffic engineering, you would probably look at something like RSVTE, or if you were looking for fast reroute, you would do a similar thing, right? So the point being here is multiple protocols providing individual features and functionality to you, right? And whether it be the interdependence worry between IGP and LDP, or just the scale problems you have with RSVP, where you can build a TE path, but you now need each node in the path, whether it be the PE node or the P node, it has to hold not just the control plane, but also the forwarding plane state. So it's not the most scalable solution either. So kind of, again, looking at that as a problem, the whole idea, again, at the protocol, the transport layer, is to simplify the transport as well. So provide the same functionality, but simplify it and put it all in the one protocol. So what you're now talking about, still MPLS encapsulation, but now running it over SR, right? So the idea now is that your label distribution is now part of your IGP. So whether it be ISSR or BGP SR, right? And then what you get inherent with that is you then get the traffic engineering capabilities, and you also get fast reroute. In terms of SR, it's termed as the topology independent loop free, right? So you get all that benefit, but you streamline the protocol and streamline the forwarding plane. And SR, sometimes a lot of people think of SR as a replacement for RSVTE. Certainly is when you start looking at controller and controllerless models, but it also is an obvious replacement for LDP, right? Because it will remove the need to run LDP and it'll streamline your protocol stack as well. Okay.
Excuse me, I have a question.
Yes.
So you only support the SR topology, the newer one, or if you're supposed to be deploying in a brownfield where there are legacy LDP and RSVP, you're still, we can add your scale out architecture there, or you only support the new protocols?
No, we support both, and I'll talk a little bit at the moment, because yeah, you're correct. I mean, when you look at this architecture, it's not going to happen as a bing bang. It's very likely it's going to have to be deployed in a brownfield, and you're going to have to interrupt with existing infrastructure, whether it be at a service level or whether it be at a transport level. So we've kind of built with that in mind. So to kind of address your question, the way we've built the whole operating system and the stack is we've separated the service, if you want to think about it. So where it's the traditional services you referred to, LDP pseudo wires, VPLS, IP VPNs, which we support, Whereas that traditional service or those newer way of simplifying the service by EVPN, right? Those are all separate from the MPLS transport. So we can map individual services to individual transports. And then to answer your question in terms of the transport models we support LDP, we support, as I spoke about earlier on, RSVTE, but we also support RSVTE as well, right? And from a services level, LDP, pseudo-wires, VPLS, IPVPNs as well. Right, so there is the capability to run this in a brownfield and migrate off as well.
Okay, I have a question. Do you have your own SDN PC controller? You're planning to have one?
Not at this point. I mean, again, we're very much of the opinion that, again, likelihoods you're going to be deploying this is going to be in a brownfield site where there already is a controller. So we work with existing controllers and provide an open API that way.
Okay.
So I'll actually demonstrate this later on. We can actually show you how you can actually migrate a service from IPVPN to EVPN, both at the service layer and also at the MPLS transport layer as well. And it becomes a very powerful and configurable way of doing it because of the way we've built the stack. So again, to take that a little bit further, the other parts of functionality we've also introduced is what we term as gateway functionality. And the whole gateway functionality is all about exactly what we just discussed there, this migration process. So where we're looking at, for example, if you take a Metro Edge Cloud sort of deployment, so a MEC deployment, where typically you'll be running some sort of leaf spine fabric, but inside the DC, it's likely to be running EVPN, but running VXLAN as the forwarding plane. But there's certainly going to be a need to break out of that fabric across your WAN or across your Metro. And you want to then learn and provide connectivity across your MPLS Metro network. What you can now do with the gateway box is the gateway box now becomes both part of the VXLAN forwarding plane and the EVPN control plane within the DC, but it also now becomes part of the MPLS transport and part of the MPLS services running in there as well. So what you're doing here now is, if you think about it, traditionally, you would have an edge or border leaf inside your DC, and you would do some sort of option A handoff, and that option A handoff would be to PE, and the PE would then be running something like IPVPN. What we're saying here with this gateway now is, I'm actually collapsing those two boxes into a single box. And I'm doing that all using merchant silicon, whereby now I have the forwarding performance of a merchant silicon chip. So that's kind of VXLAN to MPLS, but you also have similar gateways as well, where instead of the forwarding plane, what you're now doing is at the control plane level. So you think about a traditional IPVPN domain, and there's a need to then connect that IPVPN domain to a new greenfield deployment, which could be running EVPN. So the gateway now allows you as well to actually re-advertise IPVPN routes and re-advertise them as EVPN routes into the MPLS domain, into the EVPN MPLS domain, and vice versa. So this becomes a very useful migration strategy, where you can run the box within the IPVPN domain, but also allow services to be migrated off and onto the EVPN domain.
Yeah, Alex, excuse my ignorance on this question, but
Yes.
On the migrating the LDP to SR, you've got a mapping server that's listed in there. What service is providing the mapping service today?
It's just basically, I mean, if you think about it, you've got LD domain, which means that LDP is advertising the labels. And then in the SR domain, you're relying on the IGP itself to advertise the node SIDs. So what the mapping server is basically takes all the prefixes that are inside the LDP domain and then re-advertises those prefixes with a SID, which is used for SR, into the SR domain, and therefore all the nodes that are just running SR now have connectivity to those devices.
Yeah, I'm just wondering, is there a specific piece of commercial software that's actually doing the mapping server today?
It's a terminology. It's just a feature, right? It's just actually just a routing policy as such.
Yeah, so you're using inside of EOS, you're using the policy portion just to get that to redistribute.
Correct.
Sorry, it's not an actual server service that you guys are scaling up to say, okay, I just wanted to make sure I wasn't missing something there and like there was like some new product that I was completely unaware.
No, not at all. Good question. No, it's a terminology within an SR domain. So it's called a mapping server to allow you actually to connect two different separate domains together. All right. So to kind of address that question, yes, we fully appreciate that not everything's going to be greenfield. So this is why the gateway and the gateway functionality really does become key. Right? And we have sort of built out all the feature sets to allow you to migrate from one to the other. As we kind of pointed out a minute ago, I mean, with this type of architecture, scaled out architecture, software is really going to become key, right? Because you're going to need to automate. Because when you're scaled out architecture, you're potentially going to have more nodes, right? So if you look at this scaled out, you're certainly going to have more nodes because you're doing a distributed topology. So there's going to be need to automate across multiple devices, right? You can apply config, all the things we've talked about, config compliance, manage hardware and software upgrades, service enablement, bringing new boards on, boxes on board. But I suppose what we're trying to get to here is, it's all right talking about automation. Well, you've got to kind of think about when you are scaling these things out, because the whole point and the whole premise of a leaf spine architecture is the ability to onboard new leafs as you need new functionality. So the key point here is, as you onboard that new leaf, you want to make sure, although it's got extra functionality, the API stays consistent, right? The way it's streaming information is also consistent, right? So the point I'm making here is it's not just the ability to automate, it's the consistency of automate as you iterate. And this is where software really becomes critical. What you don't want is a different software for each new feature or each new platform you're driving out. And then again, if you think about it, you're scaling it out, you now need to have visibility into the state that's going on in the network itself. And when I talk about state here, I'm talking about the whole stack, right? So from all the way from the environmentals, power, optics, the kernel running on the switch, the routing state, the protocol state, the neighbors and everything else, right? You want full visibility into that, but you want visibility in a way whereby it's in real time. So you see every change happening and you can react to every change as it happens, right? So again, critical that the operating system that's running on the boxes, it's providing a state or a real-time telemetry model that's state-driven rather than a polling model or something that's only going to give you a snapshot at each point in time. So you need to give the whole network-wide visibility, you need state streaming across the box. So what I'm kind of getting to here is, like, I've talked a lot about the routing features and all the different potential use cases, whether they be at the metro edge, peering, we can now support secure peering, segment routing, TE transport. But we're doing all that functionality, but we're still doing it in the same operating system, right? Regardless of the use case here, it's the exact same operating system. So from an automation perspective, you get the exact same benefits as we had before. Same operating system, so same state-driven operating system, same APIs that Fred talked about to do all the automation. And you get that real-time state across the network of every change that's happening in the network itself, right? And I'll show you a little bit of this, give you an insight into a little of this, because what I've got is a demo lined up where I'm actually going to demonstrate the gateway. So show you this gateway functionality between IPVPN and EVPN. And as we do introduce the gateway, we can then look at the routing table and show how the routing table, as it changes, it can actually streamed off the box. And in this case, in the demo space, we'll present it into CVP. You can see the change happening almost immediately.
Excuse me, I have a question.
Yes.
Usually the solutions in the market, similar solutions in the market, they have kind of a layer, like a management system or an orchestration layer to manage, like ZTP or zero touch provisioning. So your system is totally distributed and you run it individually, each switch or router, or you also have a glue different layer where you're managing these switches or routers?
Yeah, I think you have to look at it from two parts, right? One, what we're saying here is from a control plane perspective, so the protocols that are running distributed across every single box, okay? What I'm then saying is that control plane and the software that's building that control plane is the same software on every single box. Now, to do the management of the config, the introduction of new boxes, the ZTP as you discussed, the visibility, that can be done by an open source tool, or it can be done by something like CloudVision, for example. Okay. Okay,
Yeah.
but the CVP, as we call it, Cloud Vision, CVP is not the control plane. The control plane is distributed across every node.
Okay.
Okay. All right. So let's dive into the demo. So I was going to demonstrate, as I said, was this gateway functionality. I think it's a good way of seeing how you could actually migrate to this new architecture, but at the same time, gives you sort of an insight into a little bit of CVP as such. So as I say, we support different gateways. What the gateway I'm going to demonstrate here is the IPVPN gateway. So I'm going to show how we could actually migrate services that would be running in an existing IPVPN infrastructure and then migrate them into a newer EVPN MPLS infrastructure, right? And provide seamless layer 3 connectivity across those domains. Okay. So what I've got set up in my topology is actually 3 nodes. Okay, so you really think the PE2 and 5 are the EVPN domain, and PE1 and PE2, which PE2 being the gateway, is sitting in your IPVPN domain. And what I'm going to do is show you that one is the advertisements of routes, how I can take the routes coming in from the IPVPN domain and then re-advertise them as type 5 routes over to the PE4 node, and therefore you'll see the routing table on PE5 be populated with those routes. But at the same time, what I'm also going to do is I'm going to show you how we can actually stream the routing table from the box as it receives that route, and you'll then see the route automatically being changed on the box. So what I'm going to do here is what I've outlined here in the orange is the config I'm going to add to the box to provide that. So let's see how I can start sharing. So this is Cloud Vision. And I've been in Cloud Vision, all the data from each of these switches has been streamed into Cloud Vision. So you can see, for example, if I go into E1 node, I can see what's configured. I can look at my routing table. And at the moment, because the gateway is not running, I'm only learning my local routes. Okay. Now to show you how this is, what I'm going to actually do, you might think I'm doing something in the background, but what I'm actually going to do is I'm going to add this config to the switch. But to see how quickly the routes, once the gateway is applied, how quickly the routes then obviously be advertised via BGP. But I can also then show you as soon as they are learned by that PE1 node, you can actually then see almost immediately them being streamed off the box and give you visibility via Cloud Vision of the new routing table, right? Because the point here is the streaming is now state-driven. So state-driven means that any state change that happens on that box automatically gets pushed off the box and into Cloud Vision. So I'm going to add this config, and then within Cloud Vision, you should see the routing. Sorry, 2 seconds. Okay, so I'm just about to apply the config. And you get almost immediately, can you now see the routes appearing? If it's clear on your screen. So as soon as I've applied that gateway, I'm now learning the routes from the remote end. And as soon as the box learns the routes, it's streamed the state and the new routing table straight to the into Cloud Vision. So you can see here, now you can see in the table, here's the 2 new routes being learned. And you can see that the routing table has been modified and when it's been modified. All right. So this is now gives us visibility into the state on the switch itself. All right. In this case, I'm looking at the state from a routing perspective. Okay. So I think it's one of the questions was, how do we manage, how do we control this? This is where Cloud Vision or the streaming capability of the individual software running on the individual boxes comes into play. Now, Now what I've done here is I've added the routes, and you can now see in the routing table of the boxes. I'll bring the routing table over. So you can see here, this is the PE1 box here. And you can see I've actually added the routing, and I learnt the 2 new routes, one from PE2 and the second one from the remote PE5. Right. But the important point here is at this point in time, you can see they're all being resolved over LDP. Right. So in this infrastructure, we're running LDP on both domains. And as we talked about the gateway functionality, what we can do, and we talked about the ability to configure the resolution, what I can now do is introduce, and would be a typical example of a migration step would be that I would introduce EVPN into my domain. I'd probably run LDP at the same time initially. And what I can then do is then make the software, then instead of resolving those routes over LDP, I can then introduce SR. And in my EVPN domain, I'm going to actually get them to resolve now over SR. So I'm going to introduce SR now into the topology. Still running LDP on this side, but introduce SR into this side. And the way I'll do this is because I have this configurable tunnel, and I'll do it, and again, I can do all this via Cloud Vision. Bring Cloud Vision back in. So I'm going to go to PE2 in this case. Don't die me now. So I'm going to go to PE2. I'm going to manage the config, and I'm going to change and add a feature to the config. So the way Cloud Vision works is that you have snippets of the config, or what we term as configlets. And you can see here that I've got the gateway functionality deployed, and I have the config itself, and then I have these different small configlets, which really are all about determining the route preference of how the route's going to be resolved over LDP or SR. So what I'm going to do is change it at this point in time. This one means it's going to resolve over LDP, and I'm going to change it and force it to now resolve over SR. Okay, so I'm going to apply that to the switch. I'm going to validate it, and what it goes and takes that config and then builds the whole config for the switch. And you can see now when it's built the config and it's added that new change, you can now see the change, which basically says for EVPN, so the EVPN address family, resolve it over SR, whereas previous, the right-hand side is showing me the running config, which is actually running on the box. What it's saying here for EVPN was previously run LDP. So we're going to move it from LDP and run it over SR. I'm going to save that. And once I save it, you'll see it becomes a task. And you see it popping up here as a task to be applied. And I'm going to do a similar thing on so again, this is PE5, which is an EVPN domain. I'm going to now remove it, stop it resolving over LDP, and I'm going to actually get it to force it, configure it to then now resolve over SR. So again, it's going to take that config along with the rest of the config, build a new proposed config. We can see two new lines. One is the tunnel preference. In this case, the tunnel preference is going to be SR. Plus now the change in that line, which says previously we're running it over LDP. I'm now going to run it over SR. So I save it. Save both changes. You see now, once I've saved it, it's recognized that there's two config changes to happen. I can go to the task manager. the two tasks you can see to be applied in each of the boxes, PO2 and PO5 in our topology. Click them. Change control. Change. So again, before I apply the change, it'll tell me what the change is. So again, we can see again, I'm moving from an LDP topology to an SR on PO5, and similarly on PO2, I'm moving from LDP to SR. So I'm going to approve it. It will then get applied. And we can go and look at the boxes as it gets applied. Taking its time, finished. So it's applied it to PO2, which is the gateway, and it's now going to apply it to PO5, which is the remote PE node. Now the point, what's going to now happen here is, if we go back to our topology, is once this change is complete, I've now migrated from LDP in this domain to SR. While I've done the migration, I'm also still having connectivity between my SR EVPN domain and my PE node on the remote end, which is running IPVPN in the LDP domain. Okay, so again, this is a function of the gateway to allow you to do that migration at a step as you're ready. We've migrated the service, and now we're migrating the transport. Okay, so it's now done. And you can see now, if I look at PO5, you can see now that it's still got the three routes within the VRF for the tenon, but now you can see they're all being learnt over SR. So previously it was LDP, now it's SR. So the two routes that are remote from it is learnt over SR. And if I go into P2, P2. Come on, for the delay. Sorry about a delay. And then on the gateway itself, you can see now it's resolving the route to PE1, it's resolving over LDP. And then because it's a gateway, and it's also routing into the SR domain, it's resolving the route to PE5 over SR. All right. So this is kind of like the question that was asked, how do you're never going to have a brownfield site, so gateways become very critical. So this allows you to migrate those services at the same time, the traditional VPN services, also the transport as well.
A quick question for you, Alex, just to make sure I understand, kind of the market for this. So it seemed as though this is kind of adapting like an EVPN VXLAN sort of architecture you'd find in a data center or campus, and this is like the service provider version of that, right? So it's a scalable architecture in a similar vein as those types of designs, correct?
Yes, I suppose it is. I mean, there's two parts that play here, right? One is, certainly we're seeing more and more people want to simplify the routing stack, right? So just take that as a part of the problem. So all those different VPN services we deliver, LDP pseudowires, VPLS, layer 3 VPN, right? A lot of customers are now asking as well, let's get them very complicated. There's different flavors of it. They don't all deliver what we want. We want standards-based multi-homing. So that's where the EVPN piece comes into play, right? So they want to use EVPN. They want to use EVPN MPLS, obviously. And then the physical architecture or the scaled out architecture, yeah, you're now seeing that where customers are now looking to do linear growth of the bandwidth, right? So instead of deploying a single large chassis in their POP and maybe looking now at a leaf spine architecture, but different from the DC in the fact that across that leaf spine, you're now running MPLS, right, rather than just pure IP and VXLAN.
Right. And with that, that's why you mentioned like Jericho chips. Like you couldn't do this with like Trident or Tomahawk, because feature wise, you're going to need Jericho to support a lot of this, right?
Correct. If you need MPLS functionality, exactly that, right? But I mean, interestingly, we're seeing some of the customers more in an enterprise perspective building a very similar solution. But what they're looking at is previously they would be looking at MPLS because that was the only way of delivering VPN services, right? But they didn't need the TE functionality. So we are seeing enterprise customers actually building this type of topology, but building it with IP and VXLAN because they see a benefit now of I can get my VPN services, and as you point out, I can get it at a cheaper cost because I'm just running an IP transport.
Well, I'd say one thing I bring up is that in the enterprise, we see this type of architecture becoming predominant in transit hub locations, right? As we see some of our larger enterprise customers looking at traditionally, they'd have 3 or 4 data centers geographically distributed around, say, the US or around the world. And they used to put all the telco facilities in there. Some of the more avant-garde ones I've seen have looked at the core cost centers and said, hey, let's build telco facilities and large-scale WAN aggregation into locations that have high fiber density. Let's build data centers where there's high power density and cost-effective, ecologically friendly power sourcing, and then use 100 gig, 400 gig to interconnect those data centers back to those transit hubs. This type of architecture you're describing here is exactly what I've seen some of those large enterprises deploy into those, WAN aggregation-centric, carrier-neutral transport hub, transit hub environments. So as I said, it's certainly seeing it in this evolved enterprise state as well. And I think one of the key things you've mentioned here that I really want to call back to is I spent too many years of my career suffering through what version of operating system should I put on this switch when the switch has WAN cards, LAN cards, service modules, and supervisors all sitting in it. And some of those software versions are still being used today. Like I wrote the brief on it 20 effing years ago and people are still using it. And it's like, come on, right? So in the evolved model you're describing here, I can upgrade the software and I don't have to have a least common denominator feature expression on each of the devices, right? I can upgrade from one OS to another. I can add a new device as a new leaf that adds incrementally new capabilities. And I don't have to, for instance, rip and replace and upgrade everything around it, nor do I have to deprecate the software capabilities. Right? It literally is the best of both worlds.
Correct. I mean, that is thinking about it. It's lessons learned, right? We've all been through that pain. ISSU is another one, right? We all know that you can't just automatically just hope that ISU is going to work. You have to look at the features of deploying, the line cards you're using, FPGAs running on the cards. It becomes a very complicated process. So you end up actually doing it in a maintenance window. So what you're trying to do here is actually distribute all that logic across different boxes and therefore remove the interdependence that's going on.
Right. So the goal, Doug, for these shops is really, and Alex, is to de-risk and to reduce the blast zone of a particular service that you want to be able to deploy, and the migration from one set of technologies to another in order to get you sort of across the finish line and get something up and operational quickly.
I think there's upfront risk mitigation as you describe it, Ed. Certainly there's a lot less fate sharing in this architecture, which is incredibly important. I think the real pain point that's probably hurt me and probably hurt a lot of us the most isn't, while that is a pain, and the ISSU aspects and these complicated scale-up chassis architectures have proven to be so problematic. I personally advocate for single supervisor architecture and deployments every chance I get. I'd much rather see a hard binary failure than some sort of stuck in the middle gray mode failure where control plane works and data planes melted. Right? I want really deterministic failure built into my architecture. The other thing I think enough of us are experienced enough in the industry, and by experience I mean have gray hair like me, or no hair like some of us. I'm looking at Jeff when I say that, and he's now putting his hands up like, dude, seriously, you're calling me out? I'm not even on camera. But we've all lived through multi-generational product lifecycle evolution. right? It's not the first generation of line card. It's not the second. It's the time you're doing the third generation that's not backwards compatible with the first. It requires a software upgrade. And you really need the features in the third gen. But darn it, I still have all these things connected to the first gen. And now to upgrade that requires not only new software, requires me to go back and retrofit those modules. Oh, wait, that requires new fabrics. Oh, wait, that required new supervisors. Oh, wait, that required new power supplies. Dear God, what are we doing to ourselves? It just doesn't make sense.
Yeah, and after the upgrade process, you're likely not to get the feature till you remove that old line card, right?
Yeah. I mean, there is an absolute role for modular systems that scale up. But when you start creating multi-service modular systems with highly complex forwarding pipelines that do extremely multivariate functions, the software problem in the testing matrix alone, it's impossible. I just don't see how it can even be sustained while providing the service level our customers expect nowadays for these critical production services and systems. It just doesn't work. It's been proven again and again and again to not work.
Yeah. And one other quick question. I noticed, examples of MPLS SR, and I think I'm going to beat Ed to a V6 question here, but do you guys support IPv6 SR on the for the architecture?
At this point, it's MPLS SR. We're not religiously against the SRv6, but at this point, the uptake has been, and the customer interest is most of it's been based on MPLS SR at this point.
Yeah, I think the standards groups are still arguing over size of packet payload header problems for v6 when you
header's larger than the payload. Ed, come on.
Right. We won't go down that rabbit hole. They're trying to fix some of that stuff, but I just don't know if they're going to get across the finish line in time for. On the adoption side, does it really matter? SRv6, SR MPLS?
Not anymore. Most things support MPLS these days. It did back in the days when you had a lot that didn't support it. But
right,
if you've got merchant silicon that can support MPLS, doesn't really matter.
Yeah, I think that's sort of where most people are at. And then to this architecture, if you need to switch from one to the other, you got a gateway to do exactly that if you really need to. So it sort of solves the same. Yeah, if it makes it through the standards group and they manage to make something out of it, then more hats off to them. I think there's some flexibility and interesting things they could do with extension headers around it, but whatever. That's a total in the weeds area, in my opinion.
The other thing I'll just kind of put a caveat on is I don't think this architecture or the features or the stack consolidation around BGP, EVP, NVXLAN, IPsec, MACsec, SR, and so on are everything for everybody, absolutely perfect for every design problem. I do think they address 80 to 90% of the use cases we see, especially in enterprise, but also in carrier, service provider, cloud provider, and so on. And we're seeing that, getting the right reduced complexity stack with a single operating system, with a consistent state-based telemetric, streaming and aggregation of that creates the opportunity to solve a lot more problems and solve them consistently with that. By reducing the stack complexity, we reduce the testing complexity, we increase the quality of execution and delivery for the client, right? It makes a simpler, easier to deploy, easier to manage, easier to operate architecture. I loved knowing every protocol and every acronym. And, when I took my first CCIE lab in 1998, and it's a lot harder now. And making it simpler is actually our real job, not making it harder. I know we're kind of at the end of the time here, and I figure we, might be a few minutes left to steal unless Tom wants to lay the band hammer down on me on any questions, comments, feedback, final things you guys want us to talk, all of you want us to talk about. I'm happy to address anything.
I've got a question on positioning if we have time. You're calling it cloud routing, so I just want to make sure I understand. Are you positioning this to compete against traditional routers, or is it more about adopting that cloud-like scale-up model in a POP?
I'd certainly say the latter, plus we like to use the word cloud on everything. From the initial cloud networking we did 13 years ago, which before I joined the company, I got into a tiff with our CEO about, and then I joined the company and started using it. And now I find that there's a lot of companies using the term cloud networking, so maybe we're actually prescient. But I think the second statement you made is spot on. The characteristics of the cloud, of declaratively provisioned, of easy to scale out, easy to operate. Those are the characteristics that make sense here. And we describe something that is single OS based, that has a large amount of telemetry, that is designed around a scale out architecture, and is designed to consume and maximize the value of the latest of what merchant silicon has brought to the market, staying on the leading edge of the geometries offered in the semiconductor space, is not dissimilar from what a cloud provider does on laying a single virtualization substrate on the latest and greatest silicon architectures available and making that easy to consume and scale out. That's a good question. I don't do marketing anymore, but I'll try to keep the positioning stuff in there every now and then.
Yeah, I mean, I guess I don't have a problem with the cloud. It's just the routing that threw me.
Does forward packets at layer 3.
Touche.
With lots of tunneling mechanisms available too. And Alex, check me if I'm wrong on that.
Last time I checked, it worked.
Last time you demoed it at work too, and you did it
Yep.
live. You didn't tell me you're going to do that. That was a little risk, man. I had to sacrifice a chicken in the backyard. Or at least eat a thing at KFC. Any other questions? Ed, you're usually good for one provocative, and I didn't like tee it up with you either. So
No, it's
not
good.
about
It's
V6.
good.
You cannot ask about V6 in your question.
I want all underlay and overlay, V6 only.
I want the opposite, Ed. I want V6 where you want it and the underlay what you want with them completely abstracted.
I'll compromise and just make it V6 everywhere, and then we'll call it good. Look, I mean, I think it's interesting in terms of there's a lot of complex problems that people are trying to solve today between the data center and service provider. I've seen more and more enterprises that are starting to act like service providers. So this for me is super interesting because they're my principal customer base we're really working with. So understanding how they're thinking about how they want to simplify their networks is super important. So I just sort of appreciate it. It's a little bit of a learning moment for me too, in terms of how everyone is sort of looking at this space differently than versus some of the classic models around, traffic engineering and the stuff that we were used to sort of banging our head against the wall with for years and years and years. So it's sort of cool seeing how people are thinking about it differently. So it does align with what I'm seeing, but it's good to know, get some validation that's accurate.
But what I think is going to be really powerful, if we kind of put the prognostication lens on and say what's coming, combine what Fred talked about with what Alex talked about as these two come together and say, can I take a multi-vendor, open source rooted network CI pipeline? Can I express those changes on top of a scale out routing architecture using pattern-based deployments that become declaratively provisioned, but then get cut in as gracefully as possible with well-formed interfaces between Ansible and CloudVision down to the device level. And if you kind of imagine where we see these things going, it becomes a really powerful space. Whether I'm dealing with complex edge routing problems or high-scale data center challenges or mission-critical campus environments and say hospital, clinical, assembly line environments, being able to test first, then deploy with a higher degree of assurance than I've ever had, be able to put the rigid control and version control into the templatized substrate, but then express through the abstraction of a VXLAN or a VRF or whatever VPN flavor is appropriate, the dynamic nature that the network needs to support the application or the topology construct that's necessary for voice or video or other production service. And I think that that combination becomes incredibly powerful as we move forward.